Hello friends, here we have to integrate this definite integral sin mx upon x multiplied by a square plus x square between the limit 0 to infinity. After that we have to integrate cos mx upon x square plus a square between the limit 0 to infinity. Then we have to integrate cos mx upon 1 plus x square between the limit 0 to infinity. So first we solve the first definite integral. Suppose I is given as 0 to infinity sin mx divided by x multiplied by a square plus x square dx. Suppose this is first equation. Now here we use definite integral as the function of parameter. So first we differentiate here with respect to the parameter m, because m is independent with x. Here m is independent with x, so this is the parameter. So first we differentiate with respect to m, with respect to the parameter, with respect to parameter m. So this can be written as di upon dm. This is equal to d by dm of integral 0 to infinity sin mx divided by x multiplied by a square plus x square dx. Here first we integrate the given integral with respect to the parameter m. Here m is the parameter because m is independent with x, so m is the parameter. Now this differential operator, when goes inside the integral side, it converted into partial differentiation. So this can be also written as 0 to infinity del by del m of sin mx divided by x multiplied by a square plus x square dx. So first we differentiate this sin mx divided by x multiplied by a square plus x square partially with respect to the parameter m. So di upon dm, this is equal to 0 to infinity integrate. When we differentiate this parameter with respect to the parameter m partially, so x multiplied by a square plus x square, this is the constant. So we differentiate only cos sin mx with respect to m. So we get here x cos mx divided by x multiplied by a square plus x square dx. Here when we differentiate this sin mx with respect to m, we get cos mx, and when we differentiate this mx with respect to m, so this x is constant, so we multiply this x. Now we can see here this x is cancelled out, so this can be written as 0 to infinity cos mx divided by a square plus x square dx. You can see here when we differentiate this integral with respect to the parameter m, this x in the denominator is cancelled by x in the numerator. This is the benefit. Now again we differentiate. Suppose this is second equation. Again differentiate with respect to parameter m. So this can be written as d2i by dm2 is equal to d by dm of integral cos mx upon a square plus x square dx between the limit 0 to infinity. Here we again differentiate this equation 2 with respect to the parameter m. Now this d by dm goes inside the integral side, this converts partially, so this can be written as del by del m of cos mx divided by a square plus x square dx. Now we can see here this 1 upon a square plus x square is constant with respect to m because we differentiate partially here. So differentiate cos mx with respect to m. So this can be written as differentiation of cos mx is, this is minus sin mx, And when we differentiate this mx with respect to m, we get here x is the constant and differentiation of m with m, this is 1, and is 1 upon a square plus x square, this is constant here. So this is minus sine mx upon a square plus x square. Now we can see that this integral can also be written as, here we can write this is sine mx divided by x and multiplied by x in the numerator. You can see here we multiply x in the numerator and then x in the denominator, we get sine mx upon x multiplied by x square upon a square plus x square. Now you can see here we get d2I by dm2 is equal to negative of sine mx upon x multiplied by x square upon a square plus x square between the limit 0 to infinity. Now this can be also written as d2I by dm2, this is equal to minus times 0 to infinity sine mx divided by x, and this x square upon a square plus x square, this can be written as 1 minus a square divided by a square plus x square. You can see here when we take LCM a square plus x square, so you can see here when we divide a square plus x square by when we divide x square by x square plus a square, we take here 1 multiplied by x square plus a square, so this will be cancelled out, so this is minus a square, this is the remainder, this is the quotient, so this can be written as quotient plus remainder upon divisor. So this can be written as x square upon a square plus x square can be written as 1 minus a square plus x square. When we take here LCM, a square plus x square minus a square, so this a square is cancelled out, so in the numerator we get here x square upon a square plus x square. Now we multiply this and separate these two integrals, so this can be written as sine mx divided by x plus a square is the constant, so it will be outside the integral sign, and here this is sine mx divided by x multiplied by a square plus x square dx. You can see here this sine mx upon x multiplied by 1, we get the first integral, this is sine mx upon x between the limit 0 to infinity, and this minus multiplied by minus gives plus here, and a square is constant, so it outside the integral sign. Now this sine mx upon x multiplied by 1 upon a square plus x square, we get this integral. Now we can see this is the given integral, you can see this is the given integral from 1, this is equal to I. So here we write d2I by dm2. So d2I by dm2 is equal to minus times 0 to infinity integration of sine mx upon x dx plus a square I. Here you can see this integral sine mx upon x multiplied by a square plus x square between the limit 0 to infinity, this is equal to I. Now we know that this integral, we know that integral 0 to infinity sine bx upon x, this is equal to pi by 2 here when b is greater than 0. You can see here this integral sine bx upon x, this is equal to pi by 2 when b is greater than 0. Now we put here this integral sine mx upon x, between the limit 0 to infinity, this is equal to pi by 2. So this can be written as d2I by dm2 is equal to minus pi by 2 plus a square I. Now we transform this a square I in the left hand side. We get here d2I by dm2 minus a square I is equal to minus pi by 2. Now we take common here capital I. So this can be written as d2 by dm2 minus a square I is equal to minus pi by 2. You can see here this is the first order, this is the differential equation of second order, first degree second order. So we solve the differential equation. Here we write d by dm is equal to capital D and d square by dm square is equal to capital D square. So this can be written as capital D square minus a square I is equal to minus times pi by 2. You can see that this is the second order differential equation. Here I is the dependent variable and small m is the independent variable. So we find the solution of this second order differential equation. We know that we find the solution of this differential equation. First we find the corresponding homogeneous equation. Corresponding homogeneous equation d square minus a square I is equal to 0. So here we find first here we find we make auxiliary equation, that is here we write d square minus a square equal to 0. This gives d is equal to plus minus a. So the complementary function CF is the complementary function. This can be written as here the different root plus a and minus a. So this can be written as c1 e to the power 8 a m plus c2 e to the power minus a m. So this is the complementary function of the second order differential equation. Now you can see here, now we find here, suppose that this is the third equation. Now we find here particular integral on the right hand side. So particular integral can be written as 1 upon d square minus a square of e of minus pi by 2. So this can be written as 1 upon d square minus a square, and this can be written as minus pi by 2 e to the power 0 m. Now when we find particular integral of e to the power am, we replace this coefficient in place of d. So we write here 0 square minus a square minus pi by 2 e to the power 0 m. So 0 square, that means 0 this is, and here we get minus 1 upon a square multiplied by minus pi by 2. So this gives pi upon 2a square. This is the particular integral. When we find the solution of the second order differential equation, we write here solution I is complementary function plus particular integral. So complementary function is c1 e to the power am plus c2 e to the power minus am, and particular integral is pi upon 2a square. Suppose that this is fourth equation. This is the solution of second order differential equation. Now we find the values of arbitrary constants c1 and c2. So we put here m is equal to 0 in 1, which is the given integral. You can see when we put m is equal to 0 in the given integral 1, we get I is equal to 0. Because when we put m is equal to 0 in the given integral, we get sine 0x, that is sine 0, and sine 0 is 0 here, so I is 0. Now we put again m is equal to 0 in second equation, that is in di by dm. So we get di by dm, this is equal to integration of 1 upon a square plus x square dx, because when we put m is equal to 0, cos 0 into x, that is cos 0, and cos 0 is equal to 1. So we get di upon dm is equal to integration of 1 upon a square plus x square between the limit 0 to infinity. Now we find the this di by dm, this is equal to, here we integrate 1 upon a square plus x square with respect to it. We know that this is equal to 1 upon a tan inverse x upon a. You know that here the integral of 1 upon a square plus x square, this is equal to 1 upon a tan inverse x upon a. Now we put here upper limit. So when we put here upper limit in place of x, we get tan inverse infinity, and when we put lower limit, we get tan inverse 0. Now tan inverse infinity, this is equal to pi by 2, you know that, and tan inverse 0 is 0 here. So this becomes pi upon 2a, this is di upon dm. Suppose that this is 5. Now this is di upon dm, this is equal to pi upon 2a. You can see here, we find here di upon dm, this is equal to pi upon 2a. This is the 5th equation. Now we differentiate equation 4 with respect to m. Differentiate 4 with respect to m. We get di upon dm. Here c1 is the constant, and differentiation of e to the power am is a e to the power m, and differentiation of e to the power minus am is minus a e to the power minus am, and differentiation of pi upon 2a square, this is equal to 0 here. So this is equation 6. Now we put here m is equal to 0 in equation 6. Put m is equal to 0 in 6, we get di upon dm, this is equal to ac1 minus ac2, because when we substitute m is equal to 0 in e to the power a into 0, that is e to the power 0, that is 1, and here is also 1, so this is ac1 minus ac2. Now we put value of di by dm, which is equal to pi by 2a from equation 5. So we put here pi upon 2a, and taking common a here, so we get here 8 times c1 minus c2. Now we find here value of c1 minus c2. So c1 minus c2, this is equal to pi upon 2a square. Suppose this is equation 7. Now we find here, now we put value of m, that is m is equal to 0 in 4, we get I is equal to c1 plus c2 plus pi upon 2a square. In fourth equation, we get m is equal to, we put m is equal to 0. In fourth equation, we put here m is equal to 0. So e to the power 0, this is 1 here. So c1 plus c2 plus pi upon 2a square. And we know that m is equal to 0 when we put in equation 1, that is I is equal to 0. So here we put I is equal to 0, C1 plus C2 plus pi upon 2a square. So from here we can write C1 plus C2, this is minus times pi upon 2a square. So this is 8th equation. Now we solve the equation 7 and 8. We get the values of C1 and C2. So you can see here, this is C1 minus C2 is pi upon 2a square from 7 equation. Now when we add here this 7 and 8, we get C2 is cancelled out, so 2C1, this is equal to 0, this gives C1 is equal to 0. Now when we put C1 is equal to 0 in equation 8, we get C2 is equal to, put C1 is equal to 0 in 8, we get C1 is equal to minus pi upon 2a square. So the solution of second order differential equation is, here put value of C1 and C2 in equation 4. So C2 is 0 here and C1 is minus pi upon 2a square e to the power am plus pi upon 2a square. Now we taking common here pi upon 2a square, so we get here 1 minus e to the power am. So this is the solution of the second order differential equation when we take m is equal to 0. Now we can put here, now you can see here the given integral, here I is equal to pi upon 2a square 1 minus e to the power am. So the given integral sin mx divided by x a square plus x square dx between the limit 0 to infinity, this is equal to pi upon 2a square times 1 minus e to the power am. Here you can see this is 1 minus e to the power am. Here now we can see, sorry for this, here we can see C1 is 0 here and C2 is, this is minus pi upon 2a square. So this is 1 minus e to the power minus am. Here this is 1 minus e to the power minus am. You can see here this, when we add 7 and 8 equation, we get this C2 is cancelled out, this C1 plus C1, this is 2C1, that is C1 is equal to 0. When we put C1 is equal to 0 in 8 equation, we get C2, this is minus pi upon 2a square. Now we put C1 and C2 in this equation 4, so we get I is equal to minus pi upon 2a square times e to the power minus am plus pi upon 2a square. Now we take common pi upon 2a square, we get 1 minus e to the power minus am. Now here this is the integral, given integral. Now when we find, suppose that this is equation number, so now we solve the second integral. Now we solve the second. Now you can see the given integral 0 to infinity sin mx divided by x times a square plus x square dx. This is equal to pi upon 2a square times 1 minus e to the power am. Suppose this is 1. Now we differentiate this with respect to parameter m, we get d by dm of sin mx divided by x multiplied by a square plus x square dx. Here in the right hand side, when we differentiate, we get minus e to the power minus am and minus a. As we differentiate this given integral with respect to the parameter m, both sides, so in the right hand side pi upon 2a square is constant, differentiation of 1 is 0 and differentiation of e to the power minus am is minus e to the power, and differentiation of e to the power minus am is e to the power minus am, and when you differentiate this minus am we get here minus a, and differentiation of m with m is 1. Now you can see this a is cancelled by this square and this minus is minus plus, so this is pi upon 2a e to the power minus am, and we take this differential sign inside the integral, so this converts partially, so this will be sin mx upon x multiplied by a square plus x square dx. Now we differentiate this sin mx upon x multiplied by a square plus x square with respect to the parameter m partially. So x a square plus x square, this is constant here, we differentiate only sin mx. So differentiation of this is cos mx and differentiation of mx is x, because differentiation of m with respect to m is constant, here we differentiate partially, so x is constant here. So this is equal to pi upon 2a e to the power minus m. You can see here x is cancelled out inside the integral. So this gives integral of cos mx upon a square plus x square dx. This is equal to pi upon 2a e to the power minus a. This is the second integral which we have to prove. Now we prove the third integral. Suppose that this is the integral a. Now if we put small a is equal to 1 in the integral a, we get here cos mx divided by 1 square plus x square dx. This is equal to pi upon 2 multiplied 1 e to the power minus 1 multiplied by m. So this becomes pi upon 2 e to the power minus m. So integral of cos mx upon 1 plus x square dx is equal to pi upon 2 e to the power minus m. Now you can see this integral. If we put here a is equal to 1 in the integral a, we get cos mx upon 1 plus x square between the limit 0 to infinity. On the right hand side we put a is equal to 1, we get pi upon 2 e to the power minus m. So this is the value of the given definite integral. Thank you.